All right, so welcome everyone. Today I will speak about the image reconstruction of proton CT images, and I will show my work with Barnaföldi Gergely Gábor Barnaföldi, Mónika Varga Kőfaragó, and Dávid Végrádi. So first of all, what is proton? So what is CT imaging? So during CT imaging, we take kind of two-dimensional images about an object, and we do it from lots of directions. And finally, we want to reconstruct the three-dimensional distribution of some material properties. And this material property, in case of proton imaging, is the relative stopping power of the material, which is the stopping power of the material divided by the stopping power of the water in the same proton energy. So why it is important for us? It's very important because it requires information for treatment planning to proton therapy, which is a novel treatment technique against cancer. And the use of techniques is is more and more frequently nowadays. So the motivation to improve this technique is increasing as well. So the Bergen PCT collaboration was established to develop a proton CT detector, which is visible here. And it contains two tracker layers in here and 41 calorimeter layer. Each contains more than 100 silicon pixel sensors. So it's a quite huge and complex and expensive detector. Takes years of works of a whole group of people to develop. So, and the image reconstruction is an important step of the imaging, as it has a direct effect on the quality of the final image. And this effect is how to say, nothing detectable, so it's a significant effect. So, and compared with the development of the whole detector, the development of the image reconstruction techniques requires only some person. Of course, it also requires years, but doesn't really require other sources, only computational power. And that's why I talk about this here, because it requires a lot of computational power. So anyhow, let's try to find a proper image reconstruction technique, and it's worth to optimize it as to maximize the advantage comes from the development of the proton CT detector. So first of all, what's our problem? We have a patient which we would like to imaging, and we divide the patient into small volumes called volumetric voxels with an analogy of pixels in an image. And we can imagine the imaging process like the proton goes through these voxels and has an interaction with every voxel. And this interaction can be described by beta block equation and multiplied Coulomb scattering and other effects as well. The whole imaging process can be modeled with a matrix multiplication, as it's visible here, where the A matrix contains the physics, which is these interactions, and X contains the relative stopping power of the voxels, and Y is the measured data, which is the energy loss of the protons. And some words about the size of this system. So our task is to solve this linear problem for X, and some words about the size of this problem is that the number of voxels can reach 10 to the 7, and the number of measured protons can reach 10 to the 9. So the system matrix itself is even huger. So we cannot use techniques like pseudo-inverse to solve this problem, as it would run forever. So another problem that the A matrix is very huge, and we have a fortune because it's sparse. So as each proton interacts with only a small subset of voxels, but even the non-zero elements of the matrix can reach 10 to the 12, which is as large as it's not so efficient to read it from a disk in every iteration of the solution. So we handle it as a function. So we calculate every coefficient when we have to use the coefficient, and recalculate if we would like to use again, which is a bit time consuming, but way faster than read terabytes of data in every iteration. So because we need a lot of computational power, we use GPUs and we use a multi-GPU system. And yes, we have a huge problem. So let's okay. And another main aspect of our image reconstruction technique that we don't want to read all the proton histories at the same time, as there is numerous proton histories, and we don't want to run out of memory, and we don't want to limiting our solution for an amount of protons. So we would like to be able to theoretically infinite number of protons. So and this point will dominate the solution technique, the wheel of solution technique. And of course, we would like to have a well parallelized and well optimized solution. So some words about the solution algorithm, which is called Richardson-Lucy algorithm, and comes from the field of astrophysics, where it was used to reconstruction of telescope images. And it is known as a fixed point iteration, and successfully used for emission tomography. So I hope it will be efficient for proton CT reconstruction as well. And okay, so in the beginning of this solution, we have to say to give an initial guess for the image, which is practically a unit vector in my case. And here we have a formula to update the value of one voxel based on the previous approximation of the distribution. And I will speak about the application of this formula for parallel GPU image reconstruction. So first of all, here in the left-hand side, you can see the approximation of the relative stepping power of the voxel in the next iteration. And here in the right-hand side, the first element is the previous approximation. And this second element is a fraction, which is kind of a normalization fraction based on the whole interactions in which the voxel participate. So it can be calculated pre-calculated the iteration cycle itself, and it's accelerate the solution. So let's do this. Our second modification is based on the fact that we would like to evaluate our iteration from proton to proton. So instead of calculating this summation directly, so go through this summation, we define a ratio vector which contains an element for each voxel and set it zero in the beginning of the iteration, and later read a proton and calculate this ratio for every voxel which has an interaction with the proton, and add this value to the ratio vector of the voxel. And our third multiplication is about this ratio, because this ratio has a name called Hadamard ratio, and its physical meaning is that it is the energy loss of the proton divided by the approximated energy loss of the proton based on the approximation of the distribution in the previous step. Okay, so we can calculate this ratio for the proton, and later just use it for update every element of the ratio, every element of the ratio vector for every voxel which has an interaction with the proton. And here you can see the full algorithm. So first we calculate the normalization, and after we start the iteration and use as many iterations as needed for the image reconstruction, which is typically 20 to 300 iteration. And then we read a bunch of proton histories. And first we calculate the Hadamard ratio for every proton history. And we do this in a simple way that each thread of the GPU calculates one Hadamard ratio. And as a second step, we update the ratio vector of the voxels, but we do it with a different parallelism. Like we read the Hadamard ratio serially and update the ratio vector of voxels. So update parallelly the ratio vector itself. And why do we do this? Why don't go just through? Why don't we evaluate each proton histories parallelly here as well? And the reason is to avoid race conditioning, as a two proton can have the interaction with the same voxel, and if different triads would calculate the interaction of the voxel and the proton in the same time, then they could then it could happen that two triad would like to update the same ratio, same element of the ratio vector in the same time. But as one proton can interact once with voxel, this solution avoids this race conditioning. And yes, in the end, we update the image vector. And here I would like to show some results. It's a reconstruction of a de Renzo phantom. The de Renzo phantom is designed to measure the spatial resolution of an image or an imaging system, and it contains groups of rods with the same diameter distance from each other and in a triangular structure, and there are different diameter regions, and the evaluation of this phantom is quite complicated, but a simple method just look into the phantom and let's decide in which group we can see the rods and in which group not. And here we can see the rods in 4 groups and cannot see in 2 groups, which is a reasonably good result. So yes, let's sum up my presentation. So I started a new development in the field of image reconstruction for proton CT, which is in development in the direction of the use of statistically based image reconstruction techniques for proton CT. And I applied the Richardson-Lucy algorithm, and I reached reasonably good spatial resolution, acceptable relative stepping power resolution with this algorithm. So I will continue this work and I will optimize the parameters and the performance of this algorithm. And later I plan to develop a new algorithm for proton image reconstruction, specially designed for proton image reconstruction based on maximum likelihood method. Thank you for your attention.
You told about
we may remove the okay. More.
I was talking about the non-zero numbers of the matrix, but how large is a regular image vector?
Regular image vector is between 10 to the 6 and 10 to the 7, but it really depends on the application. So it's true for proton imaging. Probably in nuclear medicine, it's usually smaller.
And the Y vector?
The Y vector is 10 to the 8, 10 to the 9 in case of proton imaging. So it's some 100 million proton history.
When you talk about tensor beam is cone beam for imaging, it's the same?
No, it's not the same. So the tensor beam means, so in case of how to say, in case of a commercial radio X-ray therapy, they use a big field for irradiating the tumor, kind of 10 centimeter times 10 centimeter or something like this. And in case of tensor beam, we use a proton beam with the diameter of 7 millimeter or something like this.
So you cannot use, for example, the Feldkamp algorithm that is normally used for the reconstruction of cranial images. Is like that.
Sorry, which algorithm?
The Feldkamp algorithm is what they use for the reconstruction of CT images for the cranial parts of the, like when you make an encephalogram. Like, what is the difference between that one and the Lucy algorithm? I guess it's more optimized for smaller things. Yeah, because you are for sure reconstructing images that are a little bit smaller.
So, do you mean filter back projection or what? Or
no, it's when you have this, you will have a lot of images in a zip format, for example, and then you make the reconstruction with this algorithm. That in your case you are using Lucia, right? I don't know if you know what is the limitation of the Feldkamp algorithm. That is the normal one that is used for reconstruction of CT images. Like
so,
maybe you know.
By my knowledge, the regular CT images is reconstructed based on image reconstruction. So based on integral transformations and the reconstruction techniques based on integral transformations. And I use image reconstruction techniques based on statistical motivation. So based on this maximum likelihood theory. And these are really different kind of algorithms. And there is two main differences. The first, so how to say, I have more flexibility to implement the, how to say, not straight line pass of the protons into this algorithm. And the other is that this algorithm works better with low statistics compared with the integral transformation based algorithms.
So actually, one of the main problems with the proton imaging that the stopping of the proton is very nonlinear in the regime where you are doing the thing. So it's not just like in the standard X-ray, you have a almost linear losing loss of energy through the body, depends slightly with the, of course, proportional to the density. But here we have sometimes real stopping in the certain area. Okay. So it's highly nonlinear. So some of the methods cannot be used in an ordinary way. So what Ákos did is this method is never used before in this way. So it's a fully, completely new thing developed by him. Further questions or remarks? There's nothing else. Let's thank Ákos again.